In the break, there were a lot of great questions. Please bring them up. I was just given permission by David that I have unlimited time to ask all the questions. Okay, so in the previous, we sort of gave a wish list of what a physicist thinks a quantum field theory should do for him, or quantum field theory that at least describes is related to something in the real world. There are a couple of things that I could mention which came up in the thing. One is the issue of unitary. When we say we want a unitary quantum field theory, we want one that is corresponds to what we might identify as a closed system. It's a closed system, it's a closed quantum system, so we want it to be unitary. You can have an open quantum system where you trace away some degrees of freedom, in which case the quantum system is not unitary, but then there is a limit where you should see it break down. For example, this has been one of the most famous ways that we learn something about the world. We knew that electrons existed. Fermi invented what was called the full Fermi interactions, which basically invented neutrinos, which had an interaction of two electrons and neutrinos. But then that theory was not unitary, and it had to break down at some high energy scale. And when that energy scale came up, we had to find the W bosons. We had to introduce the W bosons to fix that issue. So that was the idea where the theory fails to be unitary, so you add something to make it unitary. And then, the W boson with a 4 particle interaction, that also was not unitary. As you go up in energy, the theory also breaks down, and then you had to add the Higgs. Right? The reason why we needed the Higgs is because we wanted to have a unitary quantum field theory. So we couldn't talk about effective field theories that are non-unitary. We just have to remember that if we want it to be a complete system, at some point, I have to add some additional fields or degrees of freedom to make the theory unitary. So we started to talk about a Lagrangian. So we gave our wish list of what a QFT should do. We want correlation functions given some list of operators, and the partition function is something that is a machine where I give you the list of operators and it should spit out the correlation function. How can we realize this in practice? So in physics, the sort of primary object that we all love is the Lagrangian. And the Lagrangian basically is natural from point of view of locality. Okay, and as we started to discuss last time, it's some functional that depends on the position x. The function that is a field that depends on the position x, and its dependence on x is in terms of some fields that I turn on, and the derivatives of the fields. Okay, where everything is taken at the same point. And in particular, it has a dependence on finite number of derivatives. And this is an imposition of locality in general. So the Lagrangian is a classical object in a sense that when we study classical mechanics, the thing that you want to give you is the Lagrangian, and then you have the Euler-Lagrange equation that will give you the classical equation of motion. And in a quantum field theory, a Lagrangian allows us to define or give us a partition function, which is a functional of these fields, which is an integral, which is a formal expression, so it's important to say that, with a exponential I, h bar is 1, I think someone's going to yell at me for that here, times root G, if we have the space-time, times the Lagrangian as a function of these. Okay. So if I give you a Lagrangian, I can define a partition function, and we can discuss how such a partition function allows us to compute everything that we want. In general, the operator of our theory is taken by taking these fields. They have a classical phase space, which I'm quantizing in some particular way. The operators of my theory, if I take for example, the local operators, OI is going to be some function of these the fields themselves. Also, it can depend on derivatives of the fields that I have. So we construct our operators in a Hilbert space as being functions of these guys. You might also want to construct extended operators, UA, which are defined on some curve. Okay. So these extended operators themselves are going to, will have some dependence. Should I write this? Something of a sort U, which would be an integral along gamma of basically some function of the fields phi alpha of x. Okay, so if I give you a Lagrangian, you can construct a family of operators. Go ahead.
What is the integrand in exponential there?
Here?
Yeah.
That's a Lagrangian.
Or I guess
root G. Sorry.
DG.
Root square root of the matrix. If I pick a metric, this would be on whatever space time. So there's an I here. So this is given in Lorentzian space.
But why is that function of phi on the left?
Where? Here?
Z of phi.
Good. So I put z of phi here, meaning that it doesn't explicitly depend on phi because I'm integrating over phi. It was a poor notation that it's a partition function associated to these fields, right? So I should say, what does this mean? Formally in physics, this measure is not defined, and what it's supposed to be is supposed to be a sum over all possible field configuration that you can have. Okay, so it's a formal statement, and it's something that you can try to think about in practice. You can try to work. Or in particular, if you have in quantum mechanics, you can give meaning to this because you can give meaning to this. In a theory of a lattice, you can give sharp meaning to this. But in a general quantum field theory, we take this as a placeholder, some formal expression. So formally, you're supposed to sum over all field configuration, but you have to tell me what that means. So the operator that I have, you can define in principle in this way. And then from the definition, from this definition of partition function, if I want to compute, let's say, correlation functions of operators of up to some order, this I understand as some normalized thing, which I'll call Z0, which is just the evaluation of the path integral times integrating over all field configurations where the action is a weight with these operators inserted here. Okay. There's something important that happens when we're doing this computation, right? So it is true that we're thinking about them as operators that act on states and so on. Go ahead.
S is your notation for the action that you've.
So we have a Lagrangian. S would be the integral. Okay, so this is a weight factor for this. So when we insert these operators, they depend. We're treating them as C numbers. Right? It's important to distinguish that. When I'm computing a path integral, and I insert this, I'm inserting it as the actual functional of these fields, where I treat everything as C numbers. Okay. So this is an integral over field configuration. So this is a sort of fast on what the partition function does. So another thing to emphasize is that in general, this partition function can of course depend on some parameters. Let's call them how a. And then the Lagrangian will also depend, in addition to the fields, with these parameters tau A, tau B. Okay. When we say that we constructed a Lagrangian and we evaluating some partition function, usually there is an assumption that these parameters are small. They're small and they could be treated as perturbative parameters. So whenever we write down a partition function, there's an implicit assumption that we are sitting in around some locus in the parameter space, where at the origin of this locus, I have a set of parameters, tau A, that are all going to 0. Okay? So whenever we write a Lagrangian, we are assuming that we're working about this region. And what's happening in this region, this is a region where you would say that you have a classical limit or a weakly coupled field, or however else you might want to think about it. Classical in the sense that we're saying H bar is small. Okay. So something that turns out then to be true is you can have a theory which can depend on some parameters, and then you could have in principle some rather large parameter space. Some large parameter space. And often in this parameter space, you can have various points which are singular in some suitable way. And what that means is that around these points, I can define small. I can take some combination of the parameters, which I can call small, and I can expand around these things. So these are perturbative regions. Okay. And around each perturbative region here, you can have one Lagrangian 1, Lagrangian 2, some Lagrangian 3, Lagrangian 4. Okay. From this point of view, you can see that one quantum field theory can actually admit multiple different Lagrangian descriptions. Right. So this is a sort of much more recent sort of understanding that when we think about a quantum field theory, you shouldn't think of a monolithic thing. You should somehow have in mind that you have a family of theories. And whenever you write down a path integral as a functional integral of this kind, you should have in mind that you're expanding about some weakly coupled point. You can have a completely different region where you have other degrees of freedom that become weakly coupled, and then you have a different Lagrangian. So this modern perspective on quantum field theories is what leads to the term of duality. Right, where for given quantum system, we associate different Lagrangians. These different Lagrangians can have, for example, they can have different fields. Often when we talk about QFTs, and by giving a Lagrangian, we give you a gauge theory. They can also have different gauge groups. Okay. So you can think of each one of these things, they can have different fields, different gauge group, but all of this will give you some realization of the operator that I want in my quantum field theory. The thing that's always going to be the same in any duality frame is the symmetry, what we would call the global symmetry. Is same in every duality frame. This is also a fairly non-trivial statement. What that means is that while I can construct different models for the same quantum system, which can have different fields, different Lagrangians, different gauge groups, and so on, the global symmetry, which is associated to the labels that I give the operators, have to be the same in all frames. But even though the global symmetry is the same in all frames, it's not also true that whenever I give you the Lagrangian, that the full global symmetry is apparent. Some of the global symmetry can emerge when I treat at the quantum level, right? So this sort of makes it even harder that even when I'm thinking about duality structure in the quantum field theories, by writing down Lagrangians, each piece can in some cases only see a piece of the global symmetry. It's not going to be the case that every duality frame will see the full global symmetry. Each piece can see different parts of the global symmetry. And what this sort of really gets to is that when we have a global symmetry, it's really a property of the full quantum system, irrelevant whether it have a perturbative limit or not. Okay. And some of the symmetries might require you to understand operators that appear when the system is more strongly coupled than when it is weakly coupled, that you get the symmetry emerge. Any questions about this?
Does the global symmetry change as I move in this space?
So if I'm moving in this space if I define this, then the global symmetry shouldn't change, right? The global symmetry is a property of the quantum system. It shouldn't change. Okay.
Does the word global really have a meaning?
Not related to this. Not related to this space. Global, I think you're asking a different question. I'm emphasizing the word global as opposed to gauge. Because here, as I just pointed out, the different Lagrangian that can exist in different places can have different gauge symmetry. What this is emphasizing is that gauge symmetry is not a physical symmetry. Gauge symmetry is a redundancy of how we express it's a redundancy of how we try to parameterize the Hilbert space using Lagrangians. In fact, the reason why we need gauge symmetry, so that's an excellent question. It goes to the next point. The reason why we use gauge symmetry is so that we can have local Lagrangians. Gauge symmetry is a trick that allows us to write local Lagrangians to describe our system. Right? It's a redundancy. We add redundancy into our Hilbert space in such a way that we can write down Lagrangians which are local. Right? So this is really the reason why we have gauge symmetry, but it's a trick, not a physical thing. And because it's not a physical thing, what I call the gauge group can change as I move around.
So when you say you have different fields in these different regions, do you just mean that the gauge fields can be different or the fundamental fields?
Both can.
So we shouldn't talk about quantum field theory. We should just talk about quantum theory.
That's why I started in the first lecture trying to define the partition function and operator. That is the invariant thing. That's the invariant. Go ahead.
An interesting example of a theory where you would have all the parameter space covered.
Yeah. Actually, I mean, our favorite theory in the world is n=4 super Yang-Mills theory that has a exactly marginal parameter, which is the coupling. And that theory, if I write that down, I can dial it to all levels. And but the theory will admit very different descriptions. For example, that in that theory, so this point is highly non-trivial. Why is it so non-trivial? in the example of n equal to 4 super Yang-Mills, we can write, so in one representation of the Lagrangian, we can write down exactly n equal to 4 super Yang-Mill theory as a Lagrangian theory, is a gauge theory, and we know it and love it. However, if we take the parameters of this theory and we go to a different limit, something very weird happens. So this is, let's say, in d equal to 4. At a different point here, what you end up getting is what we would call type 2b string theory on ADS5 times F5. So this is to sort of highlight the maximally messed up version of this, where I take n equal to 4 super Yang-Mills. At one point, I write a nice Lagrangian theory in 4 dimensions. But if I dial the couplings, I have a different weakly coupled point, where if type 2b, I should say type 2b supergravity, on ADS5 times F5, and there are several things that have happened. One, the fundamental excitation here that I would look at is a gauge field, right, with n colors. The fundamental excitation here is a metric, is a graviton. This lives in 4 dimensions. This lives in 10 dimensions. Okay. The fields that are present here are entirely different from the fields that are present here. Right? This is a sort of a maximal version of this sort of a thing. So we should talk about a quantum system, not a Lagrangian. But although the Lagrangian is a very powerful.
You said that the reason you want to gauge is to get local Lagrangians. So does this mean you can describe something like gauge theories with non-local Lagrangians then, or?
I don't know how I would do that. I know how to write down gauge theories with local Lagrangians, but the point is that if I have if I said I have a photon with 2 polarization, the way that I know to write that theory is as as a gauge theory. You can try to undo that gauge theory, but then you might have to add an infinite number of operators to make sure that you're talking about 2 polarization. Yeah.
Sorry, I think I was confused when you say that it's the same theory when I change the parameter space. I don't know, like if I take
Good.
a theory I like and like the Higgs in the standard model, like it's different if like the mass is negative or positive, right? Like
Okay, we can
describe one thing.
So what I mean by the same theory is this is a family of theories where it's the same list of operators. The Hilbert spaces are the same. The correlation functions that you would compute from them can depend on those on the parameters, but it's the same theory in that sense.
Yes.
The list of operators that I give you are going to be the same. Even in those examples where you look at the the theory where you Higgs and you say it's spontaneously broken and so on and on. You might think about, you focus on an interacting factor. That doesn't mean that everything else wasn't there. That if you flow, you actually get a piece that's decoupled and an interacting factor. Usually you don't talk about the decoupled pieces, but in principle they're there. So that's a sort of a distinction.
So just like if I'm thinking of a Lagrangian with like parameters, what you're talking there is some particular way of moving in this space and not just moving anyway.
Yeah.
Correct.
Yeah. So and of course, if you have a Lagrangian with parameters, as you know, moving around the parameter space can be non-trivial, and there is a curvature that can measure that, which is the Berry phase. And in some contexts, you can talk about the Berry phase. This is again, this is an entirely different direction from our collaboration, but the parameter phase has curvature, which is interesting, and it can show up in quantum field theory. In particular, if I have an RG flow, you can think of an RG flow as tracing a curve on this parameter space. Right? Okay, good. So there's a distinction between global symmetry and a gauge symmetry. A global symmetry is something that basically permutes the list of the operator that I started with. A gauge symmetry does nothing to that list of the operators. In fact, all of the operators are gauge invariant operators. And because if I have a quantum system, what I want is a partition function and operators in their correlation function, I can move around in this way. So in our collaboration, we try to study global categorical symmetry. We should also keep in mind that the structure that we studying lives on top of a much larger space that we should consider. Another thing you can also do, you can turn on in a quantum field theory background fields. So these are like parameters, but they depend on the position of the space, right? And this is another way we can study quantum field theory when you have a Lagrangian, by turning on background fields and try to probe what happens as you change these background fields, and we'll say more about that. You can also have a space. You have the same way you have the space of the parameter that you can try to look at this family on top. You can also look at the space of background fields and try to study the quantum field theory on top of that. Right, and that is probably more standard that most people have seen. Go ahead.
Trying to understand what you mean by the word turn on.
Well, that's really personal.
You make them fluctuating? Is that what you
It
mean?
means they cannot fluctuate.
They cannot fluctuate.
Yeah, so background fields are fields that do not fluctuate.
No, but when you say turn them on, do you make them fluctuating?
No, turning them on, meaning I put them in by hand.
Ah.
Right, I give you a specific, let me do, I can do an example of what I mean by that.
But you don't think more that we have a space of theories and the background fields are the same for all those theories? In
So
the same way symmetry is the same for theories,
the space of background fields is fixed.
for all the theories.
It's fixed. Right. So you can move in the parameter space, or you can move in the space of background field. We still consider that the same theory, meaning that we have the same list of the operators. Right. But then the value that they take and the correlation functions will depend on where I am on the parameter space or where I am in the space of background field. So typically when we write a Lagrangian, we are sitting at the origin, the space of background. But then you can turn them on and then study. Okay, so let's talk about simple examples. So before we left last time, I was just trying to write a list of what are the typical fields that we use. We use scalars, for example. So these are fields that are invariant on the Lorentz transformation. We have vectors, and these come with two families. We have vectors with two polarizations, or they are in a 1, -1 representation. Or you can have vectors in 1, 0, 1. So these are massless. And these are massive. You can have fermionic fields. You can have fermionic fields, which are going to be given by a representation of a Clifford algebra. Of whatever is the dimension that you're working with. And you're going to have a metric tensor, which is a spin 2 field, and on and on. There is a theorem of the Coleman-Manjula theorem that tells you that if you have fields of spin greater than 2, then the S matrix is trivial. So we typically don't talk about fields higher than the spin 2, which is a metric. And supersymmetry for gravity is an exception. There are exceptions to that theorem. Big deal. So when we talk about quantum field theory, although from an effective point of view, we can include the metric tensor, we know that if I want to think about a full quantum theory involving gravity, a property that is different from a quantum field, as we discussed earlier. So we will not consider this usually, but we can try to study Lagrangians where we have these players.
It's a background field. I mean, you do fix, you need to define.
Yeah, yes, that's right. So we compute a QFT in a background, so G is a background field. Meaning, what we mean is that it doesn't have a kinetic term, it's not fluctuating, and I will talk about what that means. Okay. Okay. The simplest QFT that I can write is just a scalar where I have a Lagrangian, which I can write as d phi wedge Hodge dual of d phi. You can see this written sometimes as root g. I have to be consistent with my notation of a Lagrangian. Ibou Bah times basically the volume form. So we typically write this. So when we write this, you can add a coupling, which is a coupling of the scalar. So the partition function here is going to be this integral over all field configuration for this object. So I will often we describe this in a Euclidean space. I can see the plot d phi wedge star d. So this theory is a free theory. In particular, this integral is is an exponential which is quadratic in the field configuration. So this is a Gaussian integral. So the free theory you can evaluate exactly. It's a Gaussian integral. We don't need to go in that. But what that Gaussian integral is giving you, right? You get a width of the Gaussian integral, which is proportional to E squared. Right, where E squared is the coupling. And that width of Gaussian integral proportional to E squared, you can think of as the scale of the fluctuations of my field. That Gaussian that you get from this integral is giving you the fluctuations associated to this field, and that width is proportional to E squared. So intuitively then, if you take, for example, E to 0, right? So that Gaussian should peak to a delta function, and that's a limit where you suppress all fluctuations, as you were saying earlier. Okay. In particular, you can think about this action and try to say that I want to evaluate this path integral by taking e to infinity, e to 0. Then you have this coefficient here, which is 1 over e squared that's going to infinity. So the evaluation of this path integral localizes to a set of solutions where d phi is 0. Okay, so this is something to keep in mind because it's going to come up again and again, which is that if you have a field, there's a kinetic term which is telling you the spread of the fluctuations of the field. If I take the coupling to zero, then I localize the field and I suppress all the fluctuations associated with it. This is, some people will call this decoupling of the field, or there are various statements that you can have. Another way a field can be decoupled is that you could have mass term times phi squared times the volume form. You can also ask what happens when I take the mass to infinity. If you take the mass to infinity, then the path integral is going to be dominated by this term. And then this term, you can then just see that phi is going to be like a Lagrange multiplier. So this term being dominated also then freezes your field configuration phi to 0. So this is a statement why we say that when you take the infinite mass limit of some quantum system, you freeze the field associated with it. So this is the decoupling limit. This is the freezing limit. Okay.
Right after m squared phi.
So that's a mass term. So I can give a mass to
What did you write after the five?
Oh, the volume of the space.
Ah, okay.
Okay, volume of M. Yeah, this is it. Okay, any questions about this? So the reason why I want to, so the kinetic term in quantum field theory, the kinetic terms are important because the kinetic terms are telling you the scale at which the field will fluctuate as a quantum field, right? And it's giving you the actual weight associated to those fluctuations. Another thing that's also important when we have this kinetic term is you see that there's a Hodges star, so they also depend on the metric. Okay, so they also depend on the metric. And in particular, what it's telling you is that that dependence of the metric tells you that when you have this kinetic term, then you have, for example, a stress tensor associated to the quantum field theory, which is going to be defined in general as the variation of the Lagrangian with respect to the background metric that you have here times 1 over root g. Okay, you have this stress tensor. So because you have this Hodge dual here, that's sitting here, so this depends on the metric, the stress tensor contribution for a kinetic term is going to be, is of course not zero with kinetic terms. This tells you a couple of things, which is that the correlation function that you would compute associated to this field does depend on the choice of a background metric, okay? And in particular, if it depends on the choice of a background metric, it's not topological. That's statement one. Statement two, the fact that it's not topological also is a statement that the stress tensor is non-trivial. But as soon as I do something to decouple this field, either by sending the coupling to infinity, to zero, or adding a mass term and flowing to the IR limit, that actually sets the kinetic term to zero. So it freezes. So part of freezing the fluctuations in the kinetic term also freezes the field and sets the stress tensor to zero. And that's a case where you know, all of you heard of this term that in the low energy, meaning I'd send the mass to infinity, you can have topological order emerge. That's emerging because I'm gapping out all all local fluctuations of my quantum system that can exist. And when I do that, also I'm sending the stress tensor of that quantum system to zero. So you can have so there's no Hamiltonian downstairs. So okay, so I told you what this looks like for what this kinetic term. So what does then an operator that is topological look like? With respect to the phi field, that's I can also add the gauge field interactions. There is a so I will consider a gauge theory. So this is a massless vector. So where a mu has some gauge transformation d lambda. So this is so far we'll talk about a local gauge transformation. What that means is that this function lambda is globally defined in my space. We'll talk about later the case when lambda is not globally defined. So I can, for example, consider a theory which has a scalar and a gauge field. Here is an example of a Lagrangian for that. I can introduce I can take now phi to be a complex scalar. And I can introduce an interaction term of phi where I have this quantity d phi plus I e gauge field I. can write down a Lagrangian, which is 1 over some coupling. That means the coupling is then equal to d phi, wedge star d of phi, plus 1 over e squared times f, wedge star f, where f is d of a. So this is an example of another Lagrangian where it's a scalar phi that is coupled that has a charge under this gauge field. Okay. So this theory, we see that there's an explicit dependence of the metric here. So this is a kinetic term, which in addition to telling you the interaction with the gauge field, it also telling you that the scalar has fluctuations, which are non-zero. So this is an interacting non-topological quantum theory. We also added a kinetic term for the gauge field. So in the path integral, we're also going to sum over all gauge field configurations. And this kinetic term is also telling you that this gauge field have fluctuations, which I'm summing over. If I send E to 0, it will localize the theory to a class of solutions where F is 0, right? And that turns off the fluctuation. Here is an example of a coupling from this perspective, which is gauge invariant. You can take d phi wedge. Sorry. We can add what we would call a theta term, f squared times a theta term. This is a theta term. So this has no dependence of the metric. It has no dependence of the metric. It does not contribute to the stress tensor. So this type of a coupling is a topological coupling. Okay. Another example that you can have over here is you could see. You can add a Chern-Simons term of the sort A wedge. Maybe I don't want to use this complex scalar. I can add another scalar to this theory. Let me call it d phi. Wedge d phi. You can add a Chern-Simons term of the form A d phi wedge f, which is also another topological coupling. So both of these are examples of topological coupling. In particular, these are couplings in my Lagrangian theory that do not depend on the metric. Okay, so I can freeze these degrees of freedom by sending their couplings to 0, but I will always have such a term left over. Okay, and in particular, if I send the gauge coupling to 0, I would freeze the kinetic term, but then I have these things which would force me to sum over a flat connection. This is a non-trivial theory.
Couldn't you just like integrate that by parts and then just make the theta like axionic or something?
Good. You have choices, and those choices matter in the symmetry of the problem. It makes certain symmetries explicit, and I will talk about that. So I can what you said is that I can add a boundary term, right? So that requires integrating by parts. So I can add a boundary term. I can rewrite this as phi times f squared, right? But then in doing so, I added a total derivative. So that total derivative will matter if I put the field theory on a space with a boundary, right? And it's going to matter if what are the operators that I insert in my theory, and I will discuss this later. So from the point of view of the Lagrangian, these are equivalent, but then when I add boundaries, I have to be careful. Good. It's gauge invariant up to a boundary term. Okay. And a lot of fun happens because of that. So I can do a gauge transformation, it shifts, but then it's a total derivative, so I can forget about it from the point of view of the Lagrangian. But if I have operators that care, then this might, and we'll do an example. More question? Go ahead.
Are you just taking the phi coupling to be 1 in this last
Yeah, yeah. So, good. So the statement is that there are going to be coefficients that sit here. Okay. So the value of these coefficients cannot be arbitrary. They will be constrained by my gauge symmetry. In particular here, I've only described the local gauge transformation. I have to tell you something about the global gauge transformation. And there you have choices. Okay, there you have choices. So if I have a mu goes to a mu plus some omega, it matters where this omega sits. Okay, I can say that, for example, omega is always exact. Then that just corresponds to this gauge transformation. So this would be a case where we say that the gauge group is R. When we say we have a U1 gauge group, then omega here is going to be an element of H1 Z. Okay. So this is a case where then the gauge group is valued in R mod Z. Okay. So there is a global choices that I have to make, and that choice of a globe, and my choice of a global structure of this kind is going to constrain what these values can be. Right. So this is related to the instanton number. So that depends whether I have a U1 or R. R. I have a U1. I can. This coefficient is also constrained depending on what my global structure is. Okay, any question? Okay, so another statement to say. So here I've gave you basically simple examples of a Lagrangian. As soon as you start writing down Lagrangians, as I said from the beginning, Lagrangians make locality manifest. So all of these things are local densities that I'm writing. They all depend on one point. There are a finite number of derivatives. So this is a local Lagrangian. And the partition function is obtained by integrating this local density. So locality is completely manifest in this theory. And in particular, also, all the operators that I construct are constructed by these functions. So if I know how all of these fields talk to each other, in principle, you can tell me something about how the operators will talk. So locality is manifest. But in general, in a quantum field theory, so here I started out by giving you these terms, which we would typically call the kinetic terms. And physically, what they're doing at the level of the path integral, they're telling you how to weigh local fluctuations associated to the fields. Okay, but in general, you can start to add interactions, right? So when we write down a Lagrangian, typically we construct some Lagrangian, it's going to be, in general, we would have a term which we would have the kinetic term. And then we have a piece which we'll call the interacting term. And then we have a piece which we would call topological, but is also an interacting piece. Okay? So an example of a contribution of the topological terms are here. And one way to immediately see them is that if I vary the topological action with respect to the metric, I get 0. They don't contribute to the stress tensor. The interacting part, however, can contribute to the stress tensor and can do many interesting things. But the interacting parts, for example, is going to be, I can write it as some polynomial. Is that a question from Zoom? Of let's say the fields that I have, and all of these polynomials will have various coefficients sitting in front of them. Okay, not every choice of coefficients are possible, it turns out, in the quantum field theory. So the signs of those coefficients.
And your mic is on.
Okay. So you can get in general some polynomial with some coefficient lambda I squared and on with various coupling. These coefficients in the Lagrangian, a priori, you might think you can take them to be anything, but you can't. They're also constrained by causality and unitarity, right? In fact, if you don't fix the signs of these coefficients right, you find that you can have various things like ghost in your quantum field theory, or you can find that you violate unitarity and causality in very specific ways. So one of the things that the Lagrangian does makes locality manifest, but you might have to check more carefully of which interactions leads to unitary quantum field theories or even causal quantum field theories. So the signs of these coefficients matter. I will not say much about it because that's a whole other lecture.
I'm just curious about this decomposition you wrote, kinetic, interacting, topological. How canonical is it? I mean, how much does it depend on your local charts? If I change my local charts.
There's nothing canonical about the Lagrangian.
No, I mean the
give it-
decomposition. Like, how can you just take little pieces of it and call them topological? What if you change the local parameter around the manifold? It might throw things off.
Well, the topological part you can make sense of it. The part that does not depend on the metric, on the choice of a metric. If I scale the metric away, it will not contribute. Even that statement has caveats. It could depend on which energy scale I'm talking about. But at this level, where I just write down some effective Lagrangian, the topological part is going to be the part that does not depend on the Lagrangian.
I rephrase your
On the
statement as
metric.
saying that there's sort of a filtration and the topological part is the lowest.
I don't know how to use the word filtration, so I will not agree.
My worry is like if you change the local chart where you're defining your fields, you might pick up terms that look very different from the.
Oh, good. You're asking that, can I have counter terms that I can add that change the topological term? That's what you're asking.
Sure.
Yeah, that's what you're asking. No, that's technically what you're asking. Yeah. So you do have to worry about, but the choices of counter terms typically appears when I'm thinking about this quantum theory. You can ask that, are there counter terms that can change what I mean by the topological term? This is possible, but at this level, it's not something that I worry about. If I give you the Lagrangian, what you're really asking is, can I have an invariant definition of the stress tensor? Because this definition is a classical definition, right? At the level of the quantum theory, I should put some expectation values in various places. That's what your question is. The kinetic term is always defined, is always the quadratic piece, which is free associated to the thing. And everything else we call interaction. So the one of the statements to just highlight is that while writing down the Lagrangian makes locality explicit, it doesn't causality and unitarity will constrain these coefficients that appear here. And then that's something to think about, but I will not discuss it anymore in this lecture. So what we will do next is we will try to, hopefully I've given you a picture of how we think about quantum field theory more broadly, and the Lagrangian is a tool that we use to think about it. So what we will focus on next is trying to focus on what the case where I just have topological couplings and just focus on those topological couplings and see what we can learn from the point of view of symmetries. I'll stop here.